Good morning, champs. Today we study circulation and vorticity flux in a simple vortex flow. The goal of this example is to practice cylindrical coordinates and understand the relationship between circulation and vorticity. We consider a steady axisymmetric flow in cylindrical coordinates r, theta, and z. The velocity field is purely tangential. That means there is no radial velocity and no axial velocity. The fluid moves only around the center. The tangential velocity is given by u theta equals omega times r, where omega is a constant. This flow is called a solid body vortex because the fluid rotates like a rigid disk. A particle farther from the center moves faster, exactly like in ordinary rotational motion. Our goal is to compute three quantities: the vorticity vector, the circulation around a circle of radius r, and the vorticity flux through the disk enclosed by that circle. First, we write the velocity field. In cylindrical coordinates, the velocity vector has the components ur, u theta, and uz. In this flow, ur equals 0, u theta equals omega r, and uz equals 0. The velocity field is therefore 0 in the radial direction, omega r in the tangential direction, and 0 in the axial direction. Next, we compute the vorticity. Vorticity is defined as the curl of the velocity field. For axisymmetric swirl flow with only a tangential velocity component that depends on r, the vorticity has only a z component. This component equals 1 over r times the derivative with respect to r of r times u theta. We compute r times u theta. Since u theta equals omega r, this gives omega r squared. Taking the derivative with respect to r gives 2 omega r. Dividing by r gives 2 omega. Therefore, the vorticity in the z direction is 2 omega. The vorticity vector is therefore 0, 0, 2 omega. This means the vorticity is constant everywhere in the flow. In fact, it equals twice the angular velocity, which is a characteristic property of solid body rotation. Now we compute the circulation around a circle of radius r. Circulation is the closed line integral of the velocity dotted with the line element. For a circular path, the line element is r d theta in the theta direction. On the circle, the velocity is omega r in the theta direction. The dot product of velocity and the line element therefore becomes omega r squared d theta. To obtain the circulation, we integrate from theta equals 0 to theta equals 2 pi. Omega and r are constants, so they can be taken outside the integral. The remaining integral of d theta gives 2 pi. The circulation is therefore 2 pi omega r squared. Next, we compute the vorticity flux through the disk enclosed by the same circle. The vorticity flux is the surface integral of vorticity dotted with the unit normal vector. The disk lies in the xy plane, so the normal vector points in the positive z direction. The vorticity vector also points in the z direction and has magnitude 2 omega. Therefore, the dot product is simply 2 omega. The surface integral becomes the integral of 2 omega over the disk. In cylindrical coordinates, the area element is r dr d theta. The flux therefore becomes the double integral from r equals 0 to r and theta equals 0 to 2 pi of 2 omega times r dr d theta. The vorticity flux therefore equals 2 pi omega r squared. We now compare the results. The circulation around the circle is 2 pi omega r squared, and the vorticity flux through the disk is also 2 pi omega r squared. The two quantities are equal. This result confirms Stokes' theorem, which states that the circulation around a closed curve equals the flux of vorticity through the surface enclosed by that curve. In the next video, we will study a more realistic vortex model where rotation exists only inside a finite core, while the flow outside the core becomes irrotational. This leads to the Rankine vortex.